Activity 3, and or NOT gates, digital logic with diodes and resistors, and a transistor in the case of the NOT gate. Why do I have you looking at an oscilloscope right now? Well, the short answer is this. When you're talking about logic, everything comes down to, is something happening or is something not happening? Is it true or false? Is it a 1 or a 0? Is it on or off? And the question of whether it is a logic high or a logic low, the high and low are somewhat arbitrary. It depends on the circuit you're looking at. So if we're looking at standard 5-volt logic circuits, then the high level is 5 volts and the low level is 0 volts. But some logic circuits are a high of 3.3 and a low of 0. Others are a high of 12 volts and a low of 0. Your room light has a logic of, is it 120 volts AC or is it 0? But there's actually a third state in logic that you have to worry about, and that is the not connected to anything state. You'll hear the term tristate logic. You can be solidly connected to the high level, you can be solidly connected to the low level, or you can be not connected solidly to anything, which is the third state, the floating state. So I've made this circuit, which is nothing more than a resistor feeding an LED connected to a 5-volt DC power supply. And I have the oscilloscope probe showing you what is actually at the input to the circuit. It's floating above the board. It's not connected to anything. And if you've had much experience with oscilloscopes at all, you will notice that when it's not connected to anything, the line is not a flat line at 0 volts. It dances. If I connect the input of this circuit solidly to 0 volts, the line flattens out, and the voltage level is 0 volts. If I connect this circuit solidly to 5 volts, what is currently our logic high, an input of 1, then we have a complete circuit from 5 volts to 0 volts through a resistor, which by the way is 5.1K, so 5,000 ohms, and a logic 1 turns on the LED, a logic 0 lets the LED turn off, and if we measure the current level of the input, it is 5 volts. The problem comes where students mistakenly believe that not connected to 5 volts is the same thing as being connected to 0 volts. And if it's not connected, we go back to this fluctuating level. That fluctuating level comes from the fact that the input to the oscilloscope is a high impedance input. It is 10 million ohms. So being able to register whatever signals are being picked up at the input signal can be extremely weak. It doesn't need a lot of power to register as a voltage. This can be made much, much worse just simply by adding conductors to the input that is not connected to 5 volts, the high, or 0 volts, the low. So if I just touch it with my finger, you see something extremely interesting. You see something that looks like a sine wave. It's not a perfect sine wave. You'll notice if I move that measurement cursor down that it's 1.4 volts. That 1.4 volts is very near the turn-on voltage, the forward voltage drop of a red LED. The red LED right now is acting similar to a zener. When the voltage at the input reaches its turn-on voltage, or very close to it, It's just clamped at that voltage. Now this is a problem for digital circuits, because if you're not solidly connected to 5 volts or 0 volts, and under certain circumstances you can have voltages that fluctuate to highs that some of the circuit may consider to be a logic high, and as low as negative 3.25 volts, just by touching it with my hand. Electrical noise in your environment can cause false ones, false truths. I don't even have to touch the input to cause an effect. If I just come over to the AC power supply, which you'll notice is not actually physically connected by wires, and I turn it on and off, you'll see little pulses. If I move the trigger close to the AC waveform, but I change the trigger to be a normal trigger, which means it will only sweep if it's triggered, then we can trap some of those little impulses. Which in this case is plus and minus a half a volt. Doesn't seem like much. But what if I'm touching it with my hand, and I am, as a human being, acting as an antenna? When I turn on the power supply, turn off the power supply, all of those massive spikes cause major difficulties in digital circuits. So don't be fooled. If your input is not connected to low, not connected to high, it is not the same as a logic 0. Now, because this is a very quick and simple lab, and the 3 circuits are fairly simple themselves, I'm going to just rush through the basic design of the circuits, and then we'll come back and label it with values and do a little analysis. So we're going to have our 5-volt power supply connected to the top and bottom rail again to power all 3 circuits simultaneously. For the OR gate, we want an LED to light, giving us our verification of a 1 or 0 as an output. If one input is high, or a second input is high, or both. And we're just going to have loose jumpers that can be tied to 5 volts or 0 volts. That's your OR gate. In the case of the AND gate, our indicator LED, still connected to ground, goes to a current limiting resistor that goes all the way up to the 5 volts. This means if we don't add anything else to the circuit, the LED will be continuously on. We can, however, add 2 inputs. These 2 inputs are going to be diodes in the opposite polarity from the OR valve. If both of these diodes are connected to 5 volts, no current can flow through the diodes because they're reverse biased. So the current that is flowing from the 5 volts through the resistor to the LED keeps the LED on. Or to be put another way, if input A and input B are both high, the LED is on. 1, 1, 1. If either one of these is connected to ground, however, then the 5 volts here, passing through the resistor, on its way to the LED, that has a 1.5 volt requirement to turn on, is instead going to flow around the LED through one or both of these diodes to ground, and the LED will turn off, and the current will only flow through the resistor and the diode to ground. High and high equals high. High and low equals low. High and low equals low. Low and low equals low. The LED only lights if these two inputs are both connected to 5 volts. And finally, we come to our NOT gate, the inverter. Now the NOT gate doesn't just use a diode, it uses an NPN transistor as the inverter. Similar to the circuit for the AND gate that has a resistor that's holding the LED on until something happens at the input, the transistor inverter also functions similarly. So we have as our output another LED, which is being held on through a resistor that's connected to 5 volts. So the LED, if nothing happens to it, is continuously on as long as it's powered. It is turned off by being connected to ground, which brings this voltage, whatever it happens to be, and the LED requires at least 1.5 volts to turn on and conduct. It pulls this point of the circuit to 0 volts, causing the LED to turn off. We do that by connecting it to an NPN transistor, the collector, and the emitter to ground, controlled by whatever's at the base of the transistor. A transistor requires, just like a diode, a current limiting resistor. Otherwise we'll fry it. If we connect the input to 5 volts, current flows through the base to the emitter, turning on the transistor switch. That allows whatever current is flowing to the LED to be shunted around the LED to ground, turning off the LED. A 1 results in a 0 results in a 1. The outputs of these circuits, for the OR gate, the output is here. For the AND gate, the output is here. And the output of our NOT operator is here. Now, what are reasonable component values for this? As usual, we start off with what is our supply voltage? 5 volts DC. Each of these diodes is the 1N4001 series diode with a 0.7 volt drop. These LEDs I'm using are red LEDs, specifically because they are very low energy wavelengths and therefore very low voltages. So what are the resistor values? Well, if we have 5 volts on the supply and 0.7 on the diode and 1.5 volts on the LED, there's a 2.8 volt drop that will be seen across this resistor. Now, because this is digital logic and it's not driving anything large, and because LEDs are plenty bright even at 1 milliamp, let's say we put a 1K resistor here, that would result in 2.5 volts divided by 1000 is 2.5 milliamps. I am, for this project, going to keep the currents very low by somewhat arbitrarily using a 5.1K resistor, because I have a lot of 5.1K resistors today. So if we have 2.5 volts across a 5100 ohm resistor, how much current would that be? 1/2 milliamp. Which is well below our 20 milliamp limit. And because it's really only 0.5 milliamp, the power loss in our digital circuit is going to be extremely low. But the LEDs will be completely visible. If this resistor was 5.1K as well, which it will be, how much current flows here? So in the case of the AND gate, when input 1 is a 1 and input 2 is a 1 and the output is a 1, current will be flowing through the resistor and the LED to the tune of 0.68 milliamps. When one or both of these diodes is connected to ground, we will have a current that's slightly larger at 0.84 milliamps through a diode to ground. In the case of the NOT gate, the calculations are a little more critical, so we'll go through these step by step. Similar to the AND gate, the LED is going to be on whenever the transistor is not doing anything to it. So when the transistor is not on, then the output is on, and current is going to be flowing from the 5 volts through the current limiting resistor to the LED to ground. If we go for a 5.1K resistor as well, for the current limiting for the LED, that gives us the 0.69 milliamps. So in the case of the NOT gate, if the transistor is not on and the LED is on, the current flowing through the circuit is going to be through the 5.1K resistor and the 1.5 volt drop of the LED. Five minus 1.5 over 5100 equals 0.68 milliamps. When the transistor is on and the output is not on, the current flowing through the collector to bypass the LED is going to be 5 volts minus an ideal 0 volt drop. In practice, there's always a little voltage drop across the collector emitter, but we can, for the cases of saturating the transistor, ignore that and call this a 0 voltage drop. So it's still going to be 5 volts divided by 5.1k resistor to ground. And in that case, (0.98 milliamps), basically 1 milliamp when the transistor is on. Now there is an additional step, because the current that is flowing from the collector to the emitter is going to be joined at the emitter by the current flowing from the base to the emitter. If we're connected to ground, then the 0.7 volt drop across the base to emitter junction isn't going to matter, because the emitter is at 0 volts and so is the input, so no current flows. When we connect the input to 5 volts, however, we need to calculate an appropriate resistor to limit the current from the base to the emitter that will still result in saturating the transistor. We want it to be saturated and turned as on as possible without being ridiculous. Typically, a small signal transistor like a 2N22222 will handle up to a 600 milliamp current collector to emitter. We are only drawing 1 milliamp. The beta of a transistor like this is anywhere between 100 and 200 typically, which means whatever current we have flowing through the base to the emitter, 100 to 200 times that is going to be allowed to travel from the collector to the emitter. If we have a 1 milliamp current collector to emitter, then we only need 1/100th of that at the base. 5 volts minus the 0.7 volt drop divided by 1/100th of 1 milliamp. That means all we need at the base of the transistor is a 430,000 ohm resistor to allow 1/100th of 1 milliamp to flow from the base to the emitter. So in my kit, I don't have a 430k resistor. I could make one, but I have 100k resistors. The effect of changing this resistor to a 100k resistor means that the base current is going to be 4.3 times higher. Now that does sound wasteful, but when you understand that we're talking about microamps of current resulting in 1 milliamp of current, and we're just simply multiplying this current by 4.3 to get a standard resistor value, if anything, it's going to help guarantee that the transistor is fully saturated at the collector current that we've designed around, and minimize power loss by making sure that this collector emitter voltage drop is as small as possible. So, just to do a little sanity check on this, if we connect the input to 0, no current flows because both points are at 0. If we connect the base to 5 volts, the input to 5 volts, through a 100k resistor, we get 5 minus the voltage drop of the base emitter, divided by 100K, which is going to be 43 microamps. Through the base, times the 100 gain of a small signal transistor, means that we would get a current potentially up to 4.3 milliamps through the collector emitter, which is over 4 times what we're designing for when in the off state. So let's build this circuit. Red LED to the bottom rail. $5.1K resistor. The first diode input. And the second diode input. Making sure that the leg of one of your inputs is in a different group of 5 from the other input. But the common connection point of the inputs and the resistor are all in the same group of 5. LED. $5.1K resistor. Input diode 1. And input diode 2 to a different group of 5. For the AND gate and the NOT gate, we need that resistor to come up to 5 volts. Begins with an LED. 5.1K resistor. Connected to 5 volts. The specific transistor that I'm going to use in my circuit is a PN2222 small signal transistor. When you're looking at the transistor, make sure that you're looking at the flat front that actually has the label part markings on it when figuring out which pin is which. Taking a look at the datasheet for the PN222, you can see that the case markings are on the front. Pins 1, 2, and 3 run from left to right. Pin 1 is the emitter, 2 is the base, 3 is the collector. Emitter, base, collector. The collector is pin 3, so I'm going to insert pin 3 into the same grouping of 5 as the resistor and the LED. The base is pin 2, so pin 2 is going to be our input. And pin 1 on the far left goes to ground with a jumper. Adding a couple jumpers as inputs to our circuit, we have one jumper for the NOT gate that we will start off connected to a 0. The AND gate we will connect also to 0 to start. And the OR gate. Turn on the power supply. Now the easiest one to test is of course the NOT gate. Right now we are giving it a logic 0, it's connected to ground, and we're getting out a logic 1. Give it a logic 1, and we get a logic 0 out. In the case of the NOT gate, if we don't connect it to anything, so in theory this would be not connected, so some people would think of this as a logic 0, we do actually get a 1. On the OR gate, 0, 0, 0. If 1 is high, or the other is high, we get a high. Or if both are high, it remains high. The OR gate, when one of the wires is disconnected from 5 volts, and the NOT gate, when the input is not connected to anything, still function more or less as expected. The AND gate will not. So at the moment, we have 0 and 0 is 0. One and 0 is still 0. If one is in 5 and the other is disconnected, which you might think is the same as a high and a 0, the circuit lies to us. One and 1 equals 1. Now, although these circuits do show the concepts, they do have issues in terms of actually chaining them together and using the output of one to drive the input of others. So for example, if we wanted to use the OR gate and invert it to make a NOR gate, not OR, we could take the output of the OR gate, tie it to the input of the NOT gate. Here's the NOT gate, and here's the output of the OR gate. So now we have not only the OR gate, 1 or 1 equals 1, but if it is a 1, it's being inverted by the inverter to be a 0. If we tie in the inputs of the OR gate to zeros and make them logic lows, the OR gate now has a 0. The 0 is being fed to the inverter and being inverted to a 1. In this implementation, the circuit is working. But understand that when you tie the inputs of the OR gate to 5 volts, the output through this diode will only be 4.3 volts. So now we're passing a logic high of 4.3 volts to an input that was designed to take an input of 5 volts. In this circuit, it's capable of still operating at 4.3 volts. But if you chained multiple gates to each other, very, very quickly you would find that the loss in voltage from stage to stage made the circuit fail. You can especially see that in the case of the AND gate, where its construction means that a logic high is 1.5 volts, and a logic low, when one of these inputs is tied to ground, is going to be 0.5 volts. So instead of getting a logic high of 5 and a low of 0, the output from the AND gate is a logic high of 1.5 and a logic low of 0.7. That makes it almost useless to chain together with anything else.